Next speaker is Elizabeth Crosson.
Hi, thanks for the chance to be here and tell you about some of these results. So everything I'm going to tell you about today can be found on the archive, and it's joint work I did with an undergraduate student, and it's still ongoing, so hopefully we'll have a revised and expanded version of our preprint also later this summer. So I'm going to be talking about something called Isoparametric Inequalities, and these are going to allow us to relate the geometry of the ground state probability distribution to the spectral gap and, in fact, the low-lying spectrum of local Hamiltonians. So this generalizes a known result for Markov chains and stochastic Hamiltonians to non-stochastic Hamiltonians. And the broad goal is to further our understanding of the probability distributions that arise from non-stochastic ground states. Everybody's saying, hey, it would be great to go non-stochastic, so we would like to actually get a better handle on what these probability distributions, what features they might have that make them different. So I think the takeaway from this talk will be that so the bounds I present will reveal some ultimate limits of the idealized adiabatic model, where you do computation in the unique ground state of a Hamiltonian for a total runtime that scales polynomially in the number of qubits and the inverse spectral gap. So we'll reveal some limits of that model, but also support future directions for improving performance of quantum annealing, which, as we know, can be much more general than the quantum adiabatic algorithm. Okay, so just a bit of mathematics. So isoparametric inequalities, generally you have a space where you have some notion of distance, so you can define the boundary of a set. And you also have some notion of measure. So you can compare the measure on the boundary, the ratio of the measure on the boundary to the measure inside the set. And the example from classical antiquity is the area enclosed by a plane curve of length L. So what kind of curve encloses the most area for a given length of its boundary? Well, the answer turns out to be a circle, and that's sort of captured by this inequality. Okay, but in our finite dimensional setting, we're going to think of vertex expansion for weighted graphs. So here I have a graph which is just the 3-bit Boolean cube. And so if you pick a set, and a set of vertices, then you can speak of its boundary, which here I'm going to take the notion of the interior boundary of the set. So here's my subset, in case you can't see the labels. They're the bit strings with having weight 1 or less. And then the boundary is going to be these 3 strings here because they connect to something outside of the set. And so if you take the ratio of the size of the boundary to the size of the interior, you just get this number. And we're going to be considering these kind of ratios. So to connect this to quantum mechanics, how do we get a weighted graph out of a ground state? Well, think of the labels of some basis B as vertices of a graph. And we're going to think of the ground state as a probability distribution on these vertex labels, right? So it's important here that we're considering probabilities and not amplitudes. So even if your Hamiltonian is non-stochastic, you know, the Born rule, these probabilities are always positive. And we're going to introduce edges that come from connecting 2 vertices. So 2 basis states will have an unweighted edge between them if the corresponding Hamiltonian matrix entry is non-zero. I don't care if it's positive, negative, or complex. As long as it's non-zero, I'll connect those 2 basis states by an edge in my graph. Okay, so an example we probably all know is that if your basis is it's the computational basis and your Hamiltonian is the uniform transverse field, then the graph we just described then is this n-dimensional Boolean hypercube. Okay, and I said this in words on the previous slide, but we're going to consider the interior boundary of a set of vertices. So these are, this is this set of vertices inside of S, such that there's some vertex outside of S that they connect to through a Hamiltonian matrix element. Okay, one last bit of notation. So we'll say that our Hamiltonian H has ground state energy E that is greater than or equal to 0. You can always do this by a shift. It has this operator norm, and then also the spectral gap is notated delta H. Okay, so the theorem is that for any choice of basis, the ground state probability distribution, so if you take a subset of the vertices with less than half the total probability, then this constrains the spectral gap. So if you look at this, it depends on the range of the k-local terms in the Hamiltonian. Through the size of this boundary, you'll connect basis states that are perhaps further apart in Hamming distance, but it doesn't depend on any other details of the Hamiltonian couplings. And so what this means is that for a given distribution, the inequality constrains the spectral gap of any k-local Hamiltonian having this distribution as its ground state probability distribution in some choice of local basis. And so you might be wondering, does this really give you non-trivial results? This norm of the Hamiltonian looks like it might be, scaling polynomially with the number of qubits, but in fact we'll see this ratio can be exponentially small, and so indeed you can get non-trivial constraints out of this equation. Okay, but before we go on to examples, the generalization to higher eigenvalues. So now consider that you have some collection of subsets that are isolated, call them isolated from one another, if they're not connected through the off-diagonal matrix elements of the Hamiltonian, right? So if X is in SI and Y is in SJ, then they shouldn't be connected. All right, so if you have M of these isolated subsets and none of them contains more than half the total probability in the ground state, then the mth excited state energy will satisfy this inequality. So what this is saying is that if you have a target multimodal distribution, right, then you're going to say here's S1, here's S2, here's S3, and you're inevitably going to have at least 3 small eigenvalues when you attempt to prepare this kind of distribution. It doesn't matter if you're stochastic or non-stochastic. It doesn't depend on anything except the range of the couplings in your Hamiltonian. Okay, so to understand some of the extremes of this inequality, so you can't improve it in general. The inequality is tight for the very simple case of the ferromagnetic transverse Ising model when the z terms are just 0. So in the paramagnetic phase, the spectral gap is constant, and indeed you find that there are subsets such that this quantity is constant, and so the bound is asymptotically tight for this example. But in the ferromagnetic phase, you could take S to be the set of states with non-negative magnetization, right? And this set of states then, because your off-diagonal matrix elements connect strings that are only 1 bit flip apart, then the boundary will be the states with 0 magnetization. You have exponentially small probability of seeing those, and so if you form this ratio, you'll see that indeed the splitting is exponentially small. So also, so more generally, if you have an irreducible stochastic Hamiltonian, so this just means it's an irreducible matrix, which is satisfied by the transverse Ising model, and anything containing the transverse Ising model is a subset, then whenever the gap goes to 0, as n goes to infinity, there will exist some set such that this quantity on the right-hand side of this inequality I've been talking about will also go to 0. So you'll always have these sets with small vertex expansion. But in the paper, we also show a counterexample for non-stochastic Hamiltonians, and this is not a good thing. This shows that your gap can go to 0 even if the vertex expansion is large for every subset. So for stochastic Hamiltonians, it's kind of an if and only if. And of course, there's quantitative things going on here, which you can check the paper if you're interested. But for non-stochastic Hamiltonians, vertex expansion is a limiting factor, but doesn't necessarily guarantee your success. Okay, so just to briefly go through some parts of the proof. So in the stochastic case, you map the Hamiltonian to a Markov chain. And this is a Markov chain you can't necessarily simulate, but it still formally is a Markov chain. So the idea is that you have this stochastic Hamiltonian, we just saw the definition, and you can also relate this to a non-negative matrix G, and I've normalized it in such a way that the ground state is the principal eigenvector of G with eigenvalue 1. Okay, so the Perron-Frobenius theorem tells us that the principal eigenvector, which was the ground state of H, then has these non-negative amplitudes. And so the last thing, let omega be sort of the support of the ground state in this choice of basis, which you can always think of as the computational basis. And now define this, well, it's an operator, but in this chosen basis, it's a matrix, and in fact, it's a stochastic matrix. So remember, the property of a stochastic matrix is if you take pxy for a given x, and you sum over all y, it should sum to 1. And so indeed, if you look at this equation and sum over y, you get this projector onto omega. Sorry, sum over y here, you get a projector onto omega. And psi here, g on psi is 1, and so indeed you get that this all sums to 1. So one way to sort of compactly state what is going on here is that we've applied a similarity transformation to the Hamiltonian. So you can write this Markov chain P as a similarity transformation of a projected version of the non-negative matrix that was related to our stochastic Hamiltonian. And again, this ratio here of ground state amplitudes is something that you can't compute. So you can't actually run this Markov chain. This isn't about gaining an efficient simulation. This is going to be about using formal properties of Markov chains that we can now see applied to stochastic Hamiltonians, which I should also mention was done before by Stephen Jordan and Michael Jarrett for the stochastic case. What's new in my work is a non-stochastic generalization. And so the last thing here, from the similarity transformation, you see that the stationary distribution of this Markov chain, which also where this comes from is this was the Markov chain that Barbara and Sergei Bravi used to simulate frustration-free adiabatic computation, because in that case there's a trick for getting this ratio. So the stationary distribution is the ground state probability distribution, which is kind of exactly what you want. Okay, so the conductance inequality for Markov chains says that the equilibration time of a Markov chain, well, we formalize that as something called the mixing time, the time needed to be close in trace norm to the stationary distribution. And just, common theorem, this is closely related to the spectral gap. This factor here might be exponentially small, and so this might kick out a linear factor in n, but basically the spectral gap characterizes your mixing time of a Markov chain. So intuitively, a long mixing time is related to the presence of subsets that the Markov chain must visit, but that take a long time to escape from. So you can kind of formalize this using a quantity that is called the conductance. So here's the set S. It's got a large stationary probability, but this numerator here is sort of the probability of being on the edge and taking a step out, right? So if this quantity is small, you should expect that you get trapped in S and you have a long mixing time. So the textbook result then says that if you have a subset with less than half the total probability, the spectral gap of the Markov chain is bounded by twice the conductance for any subset satisfying this. Okay, so for the stochastic to stochastic mapping, we have a specific form of pi of x and p of xy, and if you plug those in, you can express it this way. I guess I didn't, so this is the projector onto the set S, in case I went past that notation too quickly. So if we just use that textbook result and kind of unravel, this is the spectral gap of G and is related to the spectral gap of P, I should have said that when you have a similarity transformation, it preserves your spectrum. So that's why we can use P to learn things about the spectrum of H. And so you get this result, which we could call the stochastic Hamiltonian conductance inequality. And again, that was also in an earlier work by Stephen Jordan and Michael Jarrett. So to derive vertex expansion for this case, so to go from here basically to vertex expansion, well, I've kind of written the steps here. So what you have is you're projecting the ground state onto S and the complement of S, and then you're connecting them through G. But really, because of the way we've defined the boundary, these are equal. And then because, remember, G is a non-negative matrix, psi is a non-negative vector, and so when I do this step, you're just adding more non-negative terms to this, right, when you do this, and so indeed, and then this the definition of the probability on the boundary, and so that kind of proves this vertex expansion form for stochastic Hamiltonians. So for non-stochastic Hamiltonians, this is pretty cool. So P retains many properties of a reversible transition matrix, despite having complex entries of unbounded magnitude. Okay, that might sound a little weird, but here's what I mean. Every row sums to 1. You have, again, the ground state probability distribution is the so-called stationary distribution, and you have this sort of detailed balance looking property. Actually, if P is complex, this should be P dagger, sorry. So this formal similarity to Markov chains, this is in my paper, we use this to sort of prove the exact same inequality. Now, if you look at this, and psi now contains complex magnitudes, h is complex, it's not even clear that this thing is real, but it turns out that it is. And some additional steps can be used to show the last piece. Okay, so the sort of the last content slide to go through is that if we apply this to something like a GHZ state, this state here, then we get that any k-local Hamiltonian with this as its ground state is going to have 0 spectral gap. And more generally, we can actually we can generalize that to include some error. So if you're within error epsilon of the GHZ state, then your spectral gap, sort of the important factor here is this linear dependence on epsilon, right? So if you do something like Solovay-Kitaev, you get like a, your error should scale like log epsilon. But within the adiabatic model, you kind of can't do better than this epsilon when it comes to creating the GHZ state. But hey, what about universal adiabatic computation? Well, in this case, you have to, if you want to get really close to the GHZ state, you have to pad with a bunch of identity gates, and this lowers your spectral gap. So the point is that the ancillas, the time register, increase the vertex expansion to make universal AQC work, right? So the non-stochasticity is the reason you can't simulate it, but the reason that it's useful is because you have this time register. That's the only reason that your gap doesn't become far too small, and that's what allows you to produce these kind of distributions that have very low vertex expansion, is the fact that you measure in an ancilla and it sort of projects you into that distribution. Okay, so for a given probability distribution, the spectral gap, the Markov chain, the same limit that we have for Markov chains also applies to stochastic and non-stochastic adiabatic computation. So this means that the power of AQC depends on the non-classicality of the ground state probability distribution, not the adiabatic dynamics or the spectral gap. And I think this relates to things that Mohammed Amin told us about yesterday, and also Masoud mentioned it in his talk. So these results also, I didn't have time to mention, support a modest speedup by increasing the k-local range of the off-diagonal Hamiltonian terms, because they increase the numerator of the inequality. And actually, some more complicated lower bounds on the spectral gap for stochastic Hamiltonians, sort of stochastic Cheeger inequality, stochastic vertex expansion Cheeger inequality, shows that this is like sufficient to support a modest increase in the gap. And then also, I think these use of ancillas is really promising to get around this problem of trying to sample multimodal distributions. Thanks.
Questions? Danielle?
So you focused on ground states, I guess. Can you say anything about what happens if you include excited states? Well, you did say something about excited states, but...
I did. So really, what comes out of this is that the ground state contains quite a bit of information about the entire low-lying spectrum, particularly in the stochastic case, but also in the non-stochastic case as well. And so, it depends what sort of quantum annealing general technique you have in mind, but to me it sounds like if you have, so if you have exponentially many of these strongly localized modes, then you're going to have exponentially many low-lying eigenvalues. So that may be a problem for some approaches, but it might be perfectly fine for others. Yeah.
More questions? Okay, if not, let's thank Elizabeth again.